How's it going? We are looking at the first sort of finalized version of this project I've been working on for a little over a month and a half. I call it Puck Simulator or Puck Evolution Simulator, and it is essentially a very dumbed down two-dimensional version of genetic evolution, and or at least a sort of model or example of that. Or game, I guess. It's not really supposed to be 100% scientifically accurate, but I was doing, what I could to make it as close to true as, the limitations I had. So we're going to look at an example of it running right here. All right, so you see right now we have one puck and I can click on it so we can sort of understand its behavior a little bit. So this is what I call a puck. Sort of looks like a fish. It's basically just an agent which has, for the most part, its properties are defined by its traits. And you can see the traits on the left side. I'm not going to describe all of them for the sake of time, but I essentially break it down into three main groups and then one more trait. The first group is movement traits, and so that's like how the force, its frequency of how fast it's stepping or whatever, the friction it has with the field, and then and the friction is sort of why I wanted to call them pucks in the first place, because I wanted the movement to be sort of related to how air hockey pucks might slide across a field, or I don't know what they call a rink, air hockey rink, and then the second group of traits is food tracking traits, and so we have smell and vision and melon size preference. So you can see they're eating melons. When the line to the melon is blue, that means it can see the melon and it's going straight towards it. When it's magenta, which maybe you saw earlier but you won't see as much now, it's getting a sort of general smell, a general sense of where melons are, and then going in that direction. So that's more of a vague movement, and this is more specific movement. And then if melon size preference is very low, it goes towards smaller melons. When it's high, it goes towards bigger melons. And then it has traits like sexual-based traits or mating traits. And those are basically how it relates to choosing a mate, and then afterwards the properties of their eggs. So how many eggs there will be and how long they take to mature. And then the final trait is mutation chance, which is basically with its offspring, what are the odds, what are the odds basically that some of the genes mutate and become randomized. And that's how we add genetic variation in the gene pool after several iterations and generations. So for right now, we just are watching the puck go around and eat food. As it does so, as it consumes these melons, it gains mass, but also many of its properties, like movement especially, and also the bigger it gets, it loses mass. And so if we were to watch this long enough, and maybe it's possible we're coming up on it now, it will sort of equilibrate at a certain mass because it will be gaining and losing mass at the same rate. And so we can sort of watch it just grow. And I also want to point out the colors of the puck. These are based on its traits. And so when we look at several pucks at once, we can see sort of how different genes are preferred. And so in this case, the tail is based on movement. The circle or the background sort of brown color is based on its mating traits, and then the eye, its size, the pupil size, and the color of the eye is based on its how it tracks food. And that's pretty much it. So this is right now is sort of uninteresting, but once we add another puck into the mix, it will get a little bit more interesting. And here we go. We can see, here's one, and then here are the other two. This one's not doing very well. It has very low movement traits, so power, frequency, and friction are all very, very low, so it's having a little bit of a hard time moving around. But the other two are doing pretty well. And if we were to watch these guys for long enough, two of them will decide to choose one of the others as a mate, and so it has a list of potential mates, and it sort of ranks them based on their own mass, the mass of the potential mates, the distance, how far away they are from that mate, and their standards gene here. And so once the conditions are met so that a puck thinks another is fit, and then likewise that other puck thinks that puck is a fit mate, then they will go towards each other and create eggs, offspring, which inherit traits from the parents. And so I will fast forward until we get to that point. And as you can see here, they just got very close to each other, and they were a pretty good size, and so they created these eggs. And if I were to click on one of the pucks, you can see it has green lines going towards its offspring. If I click on the eggs, it has green lines going towards its parents. And as the pucks go around, the melons they eat now, as the eggs are maturing, are divided between them and their children. And so now they're matured, they hatched, and we have 3 new pucks in the field. And if we were to watch these for long enough, they will continue the process. And at this size, it will be, here's a few more eggs. At this size, it'll be sort of a long, slow process for evolution to occur, because there's not very much food, basically, so the population is limited, and we didn't have that many pucks to start with, but we can change these values if we go back over here. And basically, let's say we can start with many pucks at the same time. Let's start with 50, and then have watermelons spawn at a pretty absurd rate, like 100 times the normal rate. And here we'll switch over, and you can see everything's happening very quickly now. You can see with all the colors of the pucks that it's there's a lot of genetic variation at the moment. And you can see, for example, this egg is being very successful. It's very big even before it's hatching. And it's pointing to its parents. This parent is pretty absurdly quick, getting everywhere at once. And while that does mean it's expending its energy very quickly, it's also very good at getting to melons. And so yeah, we can sort of just watch this for a while, and you can see what sort of traits, if we were to run this for a long time, we'll slowly start to see certain traits, and as they're represented as colors, become more prominent than others. And so I'll fast forward for just a little bit, and we can see what sort of traits are being preferred and which ones are getting weeded out. I've paused it here. We're 20 generations in, 6.5 minutes. Population of a little over 100, and we can see really well the sort of the traits, the genes of the pucks that are very successful, represented by the colors they are. And so you can see we have like a greenish, a little bit of a tinge of blue tail, pretty blue, maybe a little purple outside color, and then they have pretty big eyes, which is related to their vision and smell, and they have mostly brownish, reddish, orangish eyes, and you can see this is pretty consistent among all of the pucks here. There's a few outliers, but for the most part, all the fish look pretty similar. And we can get a look of the sort of traits that the colors and stuff are representing on the left side here. So pretty low power but very high frequency and friction. Very high vision and smell. Meal size preference looks like it's pretty a little above average, but not in the middle, 500. Standards look like on the low side, but not very low. And child count, the number of children, pretty low, a little on the low side, around the middle. Maturation looks like very long, so it looks like they want their eggs to stay, in the egg form for as long as possible. And then mutation chance, this trait is kind of hard to get much value out of. But it seems like this one has a lot of variation actually, but on the lower ends, for sure, and for the most part. So yeah, there you have it. There's an example of how evolution breeds the most efficient agents for this sort of simulation. And of course, if I were to modify values, especially if we look over here, especially the spawn chance of watermelon. So if we were to have way more watermelon or way less, then that will mean certain things are more successful. And then, of course, there are other things I could tweak. Here I have how the genes are represented. So they're on a scale of 0 to 1,000 or 0 to 999. But, they're represented by these phenotypes, which I sort of vaguely gave values to, and if I were to change these, it would have an effect. Also, if I were to change how, sexual attraction is calculated, which I have done several times, just try and get it as accurate as possible. Those will all make pretty big changes in the sort of outcomes we get. And so yeah, there you have it. There's I could also change, the size of the field and stuff like that. There you have it, though. This is on GitHub, and if you can run any Java program, you can play around with it, edit some variables if you want, or just watch it. I definitely enjoy watching it as much as possible, but I'm a little biased because I made it and it's fun to watch for me. But that's what I've been working on for the past over a month now, over a month and a half, and I'm pretty happy with I'm actually very happy with what I made. I've been able to check off just about everything I intended in the first place, and there's definitely some improvements that can be made. Some things I could add, some things I could tweak, make more efficient, things like that. But for the most part, this is it. This is what I have. So thanks for following along.